We'll jump right in and talk about adding together a ton of ones. Notice that the sum is just the number of things that we sum together here. So the more things we add up, the larger the sum gets. Therefore, in limit, this series is unbounded and grows arbitrarily large. If we scale this sum down by some constant, that is, say we add together a ton of a's that are between 0 and 1, we still get an unbounded sum. However, it grows at a slightly slower rate. As for each number of things we add together, we have that the sum of the a's is less than the corresponding sum of the ones. So this slowdown, although extremely slight, begs the question, how slow can you sum to infinity? Now, up until this point, we haven't been really mathematical at all about what we're talking about, so let's give some definitions. First off, a series that corresponds to a sequence is the sum of all the terms in that sequence. And the nth partial sum of that series is just the sum of the first n terms. So with the ones, our sequence was just 1 repeating, and the nth partial sum is n. Now we will say that the series converges if and only if the sequence of partial sums converge. And if you're not super comfortable with convergence, I have a video that motivates those ideas linked up here in the cards. And the notes of this episode linked in the description below also go into a bit of detail on the topic as well. Since we're focused on growth to infinity, we're going to want our series to diverge, and thus we only need the nth partial sums to be unbounded. So we won't need a ton of technical notions of convergence, just some inequalities. Now, let's talk about the harmonic series. That is the sum from n equals 1 to infinity of 1 over n. Notice that the corresponding sequence converges to 0. So, in a sense, this series grows much slower than if we were just to be adding ones together. And thus, it might seem likely that this series grows too slow and converges to some value. However, this is not the case at all, so let's go ahead and prove it. First, look at the 2 to the kth partial sum, and without reordering the terms, we can group together things in the following way. Notice that in each group, the rightmost term is 1 over a power of 2, and that these rightmost terms are always less than the other terms in their parenthetical group. Then we can replace the previous terms in each group with the rightmost term to get a smaller sum of 1 plus 1/2 plus 1/4 plus 1/4 and so forth. Next, with a bit of addition, we can see that the sum contained in each group is just 1/2, and there are k 1/2s in the overall sum. Therefore, we have that the 2 to the kth partial sum is greater than 1 plus k over 2. But as k increases, the sum will have no bound, so we can make it arbitrarily large. One way of thinking about the divergence of this sum is that the growth rate of the partial sums is very slow. In fact, the proof gives us an idea of this growth rate, being that in order to get more than 1 plus k over 2, we need approximately 2 to the k terms. As k increases, the number of terms required to surpass the bound grows exponentially. So we're adding a very large number of very small things together. This is great and all, but can we say this about other sequences too? That is, can we test for divergence even though the sequence of partial sums is growing slowly? The answer is yes, and in particular we can take the argument regarding the harmonic series and make it more general and fit more types of things. The crux here with the harmonic series were the power of 2 terms in the sequence, and the series that arose from taking multiples of those. We can state this general situation more clearly with the following theorem, known as the Cauchy Condensation Test. Let b sub n be a decreasing sequence such that b sub n is greater than 0 for all n. Then the corresponding series converges if and only if the condensed series given by the following converges. The argument for the proof is almost exactly identical to how we prove the divergence of the harmonic series. Now would be a good time to stop if you want to go ahead and think about this by yourself before we go ahead and write the proof on the board. Okay, so in the only if direction, we assume that the series associated with 2 to the n, b sub 2 to the n converges, and then we look at a partial sum of k terms from the series given by b sub n. We can expand and use the exact same argument from the harmonic series to show convergence. In the if direction, we assume that the series associated with b sub n converges, and then look at a partial sum of the series of 2 to the n b sub 2 to the n, which expands as so. Notice we can group terms like this, and then we can get a larger sum by replacing things with a higher index with things with a smaller index, as b sub n is a decreasing sequence. This gives this larger sum, but this is just 2 times our convergence series, and so we're done. In a sense, the process of using the Cauchy Condensation Test condenses information about the sequence into some estimation of the associated series growth rate. And so we can have series that grow incredibly slowly that still have unbounded sums. There are even broader statements that can be made about this type of phenomenon in analysis as well. For instance, Skolmilch's theorem, which I cannot say for the life of me, generalizes the Cauchy Condensation Test and gives an even broader method for condensing information about the sequence into some estimation of an associated growth rate. If you're interested, the statement and the proof are in the notes for this episode. And that is all I have for you today. I hope you enjoyed this video. If so, give it a thumbs up and subscribe for more mathematics videos. As always, I am Nathan, this is Chalk, and I will see you next time.